Learn like a pro.
You know, think about it for a second. From your electric toothbrush to the car you drive, our entire world is built on electric motors. They're literally everywhere, just humming away in the background. But they all work on this one fascinating principle, turning a totally invisible force into powerful physical motion. And today, we're going to pull back the curtain and decode that invisible engine. So that's the central puzzle, right? How in the world do we take something we can't even see, the flow of electrons in a wire, and use another invisible thing, a magnetic field, to create the very real, very powerful spinning motion that makes our world go round?
Here's how we're going to crack it. We're going to build a DC motor together, from the ground up, in 5 key steps. We'll start super small with the invisible push on a single particle. Then we'll scale that up to a wire, figure out the trick to get rotation, engineer it to spin continuously, and finally, we'll watch it do a full 360-degree cycle.
Okay, let's start at the absolute beginning. Before we can even think about building a motor, we have to get a handle on the fundamental force that makes it all possible. It all kicks off with one single charged particle running into a magnetic field. This one little interaction, it's the bedrock for everything that follows.
Now here is the first kind of mind-bending rule you need to know. When a charged particle zips through a magnetic field, the field doesn't push it forward or slow it down. Instead, it shoves it perfectly sideways, always at a 90-degree angle to the direction it's moving. And this constant sideways nudge is what forces the particle into a curve. That right there, that's the secret ingredient for creating rotation.
So, which way does it get shoved? Well, for that, we have this amazing tool, Fleming's left-hand rule. Seriously, think of it like a physical cheat code for electromagnetism. You just point your first finger in the direction of the magnetic field, your second finger follows the current, and boom, your thumb points in the exact direction of the force. It's really that simple.
And check this out. Here's the rule in action. On the left, you see positive charges curving one way. On the right, negative charges, like the electrons in a wire, curve the complete opposite way. It's the same magnetic field, they're moving in the same direction, but just by flipping the charge from positive to negative, we totally reverse the force. Remember that. This whole idea of opposition is going to be crucial in a minute.
Okay, so we get the force on one single particle. But a motor needs the force of trillions of them. So now, we're going to see how that tiny push scales up into a massive, macroscopic force that can actually do some work.
An electrical current, when you get right down to it, is just a whole bunch of charges moving together inside a wire. So as each one of those electrons gets that little perpendicular push from the magnetic field, all those tiny individual forces add up. They combine into one single, unified physical force on the whole wire. And just like that, the invisible push is now strong enough to move a solid object. A single wire is one thing, but this is where it gets really cool. What happens when you put 2 wires next to each other? If their currents are flowing in the same direction, their magnetic fields actually combine and pull them together. But, and this is the big one, if their currents flow in opposite directions, their fields clash and they push each other apart. That repulsion, that's the insight we've been looking for. So we've got a force that can push a wire. Awesome. But a simple push isn't a turn. This next part, this is the geometric aha moment. It's the super clever trick that turns a straight line push into a powerful rotational twist. The absolute genius here is the shape. A straight wire, it just gets pushed sideways. But look what happens when you just bend it into a loop. All of a sudden, the current on one side is flowing in the exact opposite direction of the current on the other. And that means one side gets pushed up while the other side gets pushed down. That perfect push-pull creates what physicists call a force couple. And that is what gives us a powerful twist. This is the moment rotation is born. Now, of course, the little turn you get from one loop is pretty weak. To make a motor that can actually do something, we've got to amplify it. We can do that by adding a ton more loops to make a coil. We can crank up the current. We can use way stronger magnets, or, and this is a big one, we can wind that coil around a soft iron core. That core concentrates the magnetic field and gives us a huge boost in turning power.
So, we have a turning effect, which is great, but we also have a problem. Right now, this loop would just turn about halfway and then get pushed back the other way. It would just rock back and forth, not spin all the way around. This is where some really clever engineering has to step in to solve this rotation problem.
So let's take a look at the full anatomy of our motor. We recognize the magnet, the copper coil, the iron core, but look at that weird little copper ring at the very end. The part labeled the split ring commutator and carbon brushes.
That little gadget? That's the brains of the whole operation. That is the device that solves our spinning problem.
So here's the snag laid out plain and simple. Once the left side of our coil spins all the way over to the right side, the force on it would flip and it would just push it right back where it came from. To keep this thing spinning in one continuous direction, we have to find a way to perfectly reverse the current flowing through the coil at the exact moment it finishes a half turn.
And the split ring commutator is the brilliant, elegant solution. It's just a copper ring that's been split in half. It rotates with the coil, while these stationary carbon brushes feed it power. And with every 180-degree turn, each half of the ring swaps which brush it's touching. This simple mechanical action physically reverses the flow of current into the coil with perfect timing every single time.
But you might wonder, why are there gaps? What are they for? Well, think about it. If that ring was solid, for a split second, the positive and negative brushes would both touch the same piece of metal, creating a massive short circuit. Those gaps act as a crucial safety switch. They briefly break the circuit at just the right moment to prevent that from ever happening. All right, we've got all our pieces on the board, we understand the physics, we have the engineered components. Now let's put it all together and watch our DC motor complete one full, continuous 360-degree cycle.
Let's walk through one full rotation. When the coil is horizontal, the circuit is live, and we get maximum clockwise force. Then, as it rotates up to the vertical position, the brushes hit the gaps in the commutator, the dead zone. But then, as it passes the vertical, the magic happens. The commutator has flipped the current, so even though the wires have switched sides, the forces have also reversed, which keeps the turning direction the same. It keeps pushing clockwise. The timing is just perfect.
Now you might be asking yourself, wait, if the circuit is open and there's no force at that vertical spot, what stops it from just getting stuck there? And the answer is just one word: momentum. The coil has built up kinetic energy. It wants to keep spinning, and that momentum acts like a bridge, carrying it right past that dead zone until the brushes reconnect and the power kicks back in. So our motor is spinning, but how do we control its speed? Well, we add a rheostat, which is really just a fancy name for a variable resistor. By turning the dial, we increase the resistance, which limits how much current can flow to the coil. Less current means a weaker magnetic interaction, a weaker turn, and a slower motor. It's basically the throttle for our engine.
So when you boil it all down, a motor is really this beautiful symphony between three key ideas. First, you have the physics, that fundamental 90-degree push. Second, you've got the geometry, the simple loop that cleverly turns a push into a twist. And third, you have the engineering, that brilliant commutator that masterfully reverses the current, basically tricking physics into giving us a constant one-way spin.
And that really is the ultimate takeaway, isn't it? The power of a motor comes from magnetism, sure, but the genius of a motor, that lies in the timing. It's a perfectly choreographed dance between force and reversal that turns a simple push into relentless, continuous rotation.
So we've seen how we can use electricity and magnetism to create motion, which, of course, leaves us with one final, fascinating question to chew on. If that's how a motor works, how could you use motion and magnetism to create electricity? In other words, how does a generator do the exact opposite of the machine we just built?